Hi guys, we're going to get started today with our lecture series on stellar evolution. I'm going to try and break this up into three separate little lectures for you so we don't have to do quite as much at any one point in time. All the questions are listed together though on the Google Doc that's on It's Learning that you guys can fill out as we go along. So today we're going to try and tackle questions 1 through 17 if you're following along there. What you're looking at here is a beautiful picture of what's known as a planetary nebula, and it was taken with the Hubble Space Telescope. The name's a little bit misleading because it really doesn't have anything to do with a planet. In the center of that picture, what you can't see is very likely a white dwarf star, and this is a picture of the end state of a medium mass main sequence star. This is probably pretty similar to what our sun is going to do when it goes out. So we're going to go along and see how stars evolve here. So stars are kind of constantly radiating energy by converting hydrogen to helium in their cores. If a star's in the main sequence, that's what it's doing. So stars are really a balance of two forces. There is the force of outward pressure from the nuclear fusion, and it's constantly balanced by the inward pull of gravity. Those two forces, when they're balanced, the star is said to be in hydrostatic equilibrium. So if you take a look at your questions here on your paper, number one says, what's the primary factor that determines how long a star is going to live or how it will evolve? That primary factor is its mass. The more mass it has, it will evolve very differently than a medium mass or a lower mass star. And there's other things that are involved too. For instance, how well the gases are mixing in the star, and a lot of other stuff that happens. But really, even those things depend mostly on the mass of the star. So we're going to focus a lot on mass. We're going to start with low mass stars. Low mass stars are stars that are anywhere from about like 8 or less than 8 solar masses. So that's solar masses are the mass of our sun. So we'll talk, and that's the little funny little circle dot there is underneath the M, that little subscript. That means the sun size. So we kind of put everything in relation to our sun because it's an easy way to talk about the sizes of stars. So anything less than about 8 solar masses is considered a low mass star. So uh, let's take a look here. Low mass stars are going to evolve very, very differently than high mass stars. If you're looking at the question number 2 on your paper, it says, what are the two forces that a star has to constantly balance? Those are pressure and gravity, and we just mentioned that, but the outward push of pressure against the inward pull of gravity. As soon as a star fails to provide enough pressure outwards, gravity wins. We like to say that gravity always wins for a star. It is true. In the end, gravity defeats the outward pressure that's being produced by nuclear fusion. Because eventually all stars run out of fuel. So we're going to kind of move along here and take a look at what the differences are between some different mass stars. So we've got a little graph here, a little table of the spectral types of stars, the O, B, A, F, G, K, M stars that we learned a little bit about that are on the HR diagram. And it's showing you here the different masses. Up at the top are the really high mass stars, like mass of 40 solar masses. At the bottom, we've got stars that are very, very small, like 0.21 solar masses. That's tiny, tiny. And then we can look across there, not only at how bright they are, their luminosity. High mass stars are incredibly luminous, but also look at the amount of time they live for. So their time on the main sequence is essentially the time that they're fusing hydrogen into helium, and it's when that hydrostatic equilibrium is balanced. So for an O-type star that's like 40 solar masses, we're looking at 8.0 times 10 to the 5 years. So that's not very long. Think 800,000 years for a star to live. The biggest, the brightest stars burn out the fastest. The smaller stars If we look down there towards the bottom, in M5 is at 2.7 times 10 to the 11 years. That would equate to 270 billion years. 270 billion years. Think about that. It's older than the age of the universe by a lot. So really low mass stars, some of them could have evolved early on in the formation of the universe after the Big Bang, and they're still with us today. In fact, they're going to be here a very, very long time. Looking at our sun there, our sun's a G2 star, one solar mass, of course, one solar lumen, because it's our sun. And if we look at its lifetime should be about 1.0 times 10 to the 10 years. That's 10 billion years. Now it's about halfway through its lifetime. So 4.5, 4.6 billion years ago, our solar system, our star, the whole thing, the Earth formed. So we're about halfway through our life on the main sequence. Stars can live anywhere from thousands, hundreds of thousands of years to billions of years, right? So big range there, hundreds of billions of years. Okay, let's see. We answer the questions here. Yeah, so which stars live the shortest lives? The shortest lived stars are the largest stars, the ones with the most mass, like O5 stars. Um, the reason for that is, like I said, if they have a higher mass, that means they have a higher temperature, which means that they have faster nuclear fusion. They burn up their fuel way more quickly, way more rapidly than lower mass stars. Okay, and there's some other funny things that can happen too. Lower mass stars can have more mixing of their fuel, so they don't tend to run out, whereas a larger mass star will pretty much burn up what's in its core and never be able to fuse the outermost layers of the star. So it can't really use everything about how big a star is. It doesn't actually get to use all the fuel that it's got. For most stars, they get to use the fuel that's down there deep in their core. But we'll talk a little bit more about that as we go along here. Our next question is about the HR diagram. So we're on to number 4 here. What does the HR diagram show? There are a number of ways that you could answer this question. Let's at least just look at the axes here. What the HR diagram is, it's a scatter plot of stars primarily based on their luminosity. So that's in some respects how bright they are, and their surface temperature. So at least get down that it's based on their luminosity. It's a plot of stars based on their luminosity and their temperature. Okay. So luminosity is a little confusing because it's brightness, yes, but it's kind of like qualified brightness. So you got to remember, the further away a star is from us, the dimmer it is, right? So luminosity is when we've taken and we've kind of corralled all those stars to the same distance. How bright would they look then? So that's kind of a way to think of luminosity. It's actually how much is radiated per square meter of the star's surface. So it's a little different than brightness, but we can kind of call it the same thing for our purposes here. So as you look at the HR diagram, it's really plotting stars based on their luminosity and their surface temperature. And if you remember, surface temperature is that OBAFGKM system that was developed, right, a long time ago by the computers. Right? We're talking about stars here, and got the HR diagram there. Let's take a look at the main sequence. So the main sequence is that stretch of stars that stretches from the top left-hand corner all the way down to the bottom right-hand corner. It's like a string of stars. And when the HR diagram is being first put together by Hertzsprung and Russell, the two guys who came up with this, they noticed this pattern of stars in this sort of line here in the middle, and then they had all these weird outliers. And this diagram's labeled with what we understand now. The main sequence, as it turns out, really just represents a line where stars are in that equilibrium where their gravity and their pressure is balanced. In other words, they're fusing hydrogen into helium. So that's what a star is when it's on the main sequence. Okay, a star, any star will spend most of its life on the main sequence. So you can put those things down there for what does the main sequence represent, and what are they fusing? They're fusing hydrogen into helium, so the hydrogen's becoming helium as they're on the main sequence. So our sun's there, right, kind of in the middle of the main sequence. If you look at this, the HR diagram, it's a little bit funky. If you look down there at the temperatures, it doesn't go evenly across the bottom there. It's been stretched and squished in order to fit things properly on here and make them look a little bit better. Otherwise, we have some big gaps in the diagram. So take a look there. That is the main sequence. Let's look at how stars move on to the main sequence. So stars start out their lives as a cloud of gas and dust, and that cloud of gas and dust has to somehow compress to start collapsing. And there's lots of ways that can happen. Primarily, a supernova explosion nearby can send a shock wave through a giant molecular cloud of gas. Maybe two molecular clouds will collide. A lot of different ways that this might occur, but eventually gravity takes over and all the gas and dust that's out there in our galaxy, the Milky Way, starts to collect in a certain area and coalesce to start to form stars. So when we look at the HR diagram, we're going to keep looking at this to follow stars throughout their lives. Now, I'll say this again here in a second, but remember, the HR diagram doesn't represent stars actually physically moving through the sky. Okay? The HR diagram represents where a star is at in terms of its luminosity and its temperature throughout its lifetime. Okay? So, actually, we just answered, we answered number 6 there. Okay? So when we say that a star moves onto the HR diagram, what does that mean for the star? Is it actually moving in space? No, it's not actually moving in space. What's happening is that we're just now able to graph it on the HR diagram, right? Because as a star starts out, it's slowly heating up. It doesn't become part of the HR diagram technically until it ignites fusion in its core. Once it starts to fuse hydrogen, the star brightens and it comes onto, we say it falls onto the main sequence. Because before that, it's dark. I mean, it might be emitting some heat, but it's pretty dark to us before it falls onto the main sequence. But it doesn't really move through space, right? It just enters a different spot on the HR diagram. So, what determines where it lands on the HR diagram? Its mass. The more massive stars end up further up on the diagram on the main sequence. Lower mass stars end up lower down on the main sequence. And then we'll kind of see how they evolve from there. This diagram's got a little bit of extra stuff on there. The R with the little subscript of our sun there is representing the radius in terms of solar radii. So that's like how big it is in comparison to the sun. Okay, just in radius, or you think diameter, right? 2 times that's the diameter. So our sun lands right on the 1 solar radius line there. Okay, kind of move along here. So, is there an upper limit to how big a star can be? How massive a star can be? Yes, absolutely there's an upper limit. And there's some reasons for that. First of all, really, really big clouds, as they're collapsing, large clouds of gas and dust that are out in space, as they're collapsing, they start to rotate and they tend to fragment. They might fragment into 2 or more stars before they actually come together. Stars that are forming that are roughly like 100 solar masses or bigger, if they're able to start to form that size, they tend to be very unstable as they form, which means they get so hot that their solar wind can actually blow away most of their mass, and so they end up being a lower mass star when it's all said and done. So even though they might start out forming larger, they end up smaller just because they're so darn hot, they blow away their outer layers. There's not as much gravity to hold them in because they're further away from the center, and it gets blown off. So, so there is an upper limit to how big a star can be. Okay, let's work on through here. Up at the very, very top of the diagram, on the main sequence are these really big, bright blue stars. And you notice this is color coded because these stars, the temperature of a star relates to its color. So big, bright blue stars are very, very hot. Down on the lower side of the HR diagram are the lower mass stars, lower right-hand side. They are redder because they are cooler, but it's very difficult for us to find these smaller stars. In fact, even though we'll find out here in a minute, they're far more common than their bigger mass brethren. The bigger mass stars are the ones you actually see. When you look up at the night sky, you don't see those little red dwarfs. They're way, way too tiny to see with the naked eye. You need a telescope. So most of the stars you see are not actually the most common stars in the sky. So if a star is small enough, what's forming a star is, say, 0.08 solar masses or smaller. It's too small to actually ignite fusion. And we have a term for these. We call them brown dwarfs. They kind of represent this this like neat little evolutionary trend from planet to star. So consider this for a second. The outer planets in our solar system are gas giants, right? So they're composed entirely of gas. Well, what gas? Well, mostly hydrogen, which is what our sun is made up of. So had they gotten larger, for instance, Jupiter, if it had gotten, like, I don't know, maybe 3-4 times as large as it is, I mean, it's quite a bit, we could have had a second star. In fact, most star systems are actually binary star systems, actually two rather than one. But if it had gotten larger, we would have had a second star. So Jupiter's not a brown dwarf, but a bigger star, a bigger planet, if you will, we might call a brown dwarf. It gets hot, but just not quite hot enough to ignite fusion. Now, do they exist? Do brown dwarfs exist? We have actually found them now. It was quite the search for these things because they're very difficult to find. They don't emit really any light other than in terms of thermal light, so they're hard to see, but they have been found. So brown dwarfs do exist. Anyway, we find, if we look out into space, there's lots and lots and lots of red dwarfs. So like I said, there's probably far more brown dwarfs than we've ever actually discovered. They're just hard to find. Okay, I think we've answered number 8. Let's move on along here. Oh, there we go. There's the red dwarfs there, down at the very bottom. Okay. So the process that causes a star to leave the main sequence, to understand that, we've got to understand a little bit about how stars evolve and what they do. Over the course of their lifetime, as a star leaves the main sequence, it's going to increase in luminosity. It's going to get considerably brighter. It's also going to get larger, and that's really the reason it gets brighter. What's happening inside the star is its fuel's changing. So in order to maintain this balance between pressure and gravity, a star's always got to be fusing something down there in its core. And as it does that, the pressure pushes outwards and it supports the star against the gravitational pull. So as that stuff starts to run out and not as much pressure is produced by the fusion, the gravity starts to collapse and win. But that won't be the final story. Let's kind of continue along here, and we'll try to answer number 9 here is the one that we're on. The process that causes a star to leave the main sequence. So I've tried to outline it for you here, but essentially, as the hydrogen gets used up in the core, it's going to eventually run out. Okay? It's becoming helium. All right? The helium's accumulating down there in the core. We actually call it helium ash. Now remember, none of this is actually in any way akin to burning anything like you would with a chemical reaction like fire. It's just that astronomers are kind of poetic, and we just refer to nuclear fusion as burning, but it is not a chemical reaction, right? It's a nuclear reaction. Anyway, the helium is being produced, and it's settling down there into the core as ash. And there becomes sort of a problem here because the pressure of those atoms, those nuclei, are what's supporting the star. That gas is pushing outwards to support the star from the heat that's being produced inside. Now, one helium nucleus can exert the same pressure as a hydrogen, right? But remember, a helium has two protons, a hydrogen only has one, right? So it takes two hydrogens to make a helium. So in the end, there's less nuclei present down there to create the pressure. So here's the situation. Let's kind of wrap it up here. What happens as a star leaves the main sequence? Number one, it starts to run out of hydrogen. Okay, it burns up its hydrogen in its core, and that causes less pressure. So less outward pressure, and then that causes gravity to start to contract in. And as gravity contracts inwards, the core gets hotter, right? So the reactions actually speed up. Um, and then that hotter core makes the star more luminous. So it gets brighter. And remember, the HR diagram is determined by both temperature and brightness, luminosity. And so the star starts to peel off the HR diagram, and it peels off upwards and to the right. So think about that for a second. As that star is heating up, okay, the star is expanding, it's getting larger, and because it's larger, it gives off more light, so it gets more luminous. Okay, so that's what causes it to go up the main sequence, or up the HR diagram. What moves it to the right is that as it expands, the surface actually cools. Now, that's a little bit hard to understand sometimes because inside the star in the core, it's getting hotter. But when you expand a gas, the outer part of the star, the part that we see and we measure for temperature, is actually cooling off. So the star gets more luminous and more red. Okay, so as stars move off the main sequence, they move over towards what we call the giant and the supergiant stars. And many of those are red, like red supergiants, things like that. Okay, so it's essentially, if we can sum it up there really quick, the star runs out of hydrogen, uh, and gravity begins to take over, the core heats up, the star expands, gets more luminous, gets cooler on the outside, and that's what causes it to move off the main sequence. Okay, where are we at here? There we go. So if we look at the main sequence, there's another HR diagram. Lots of ways to draw this here. Um, so let's look at let's look at where the sun is here. It's down there, kind of near the bottom. It's a lower mass star. Uh, its lifetime is going to be about 10 billion years on the main sequence. So we're about halfway through. So how much longer do we have on the main sequence? We have about 5 billion-ish years. About 5 billion years till we move off the main sequence. In 5 billion years from now, the sun's going to be 2 times as luminous as it currently is. That's considerably more radiation coming off of our sun for us. So even though the surface will be cooler, there is so much more of it that it's going to evaporate our oceans and cook off our atmosphere. That's what's going to happen to the Earth. Now the other planets, the inner planets, Mercury and Venus, they're actually going to be inside the sun as it expands. So it's going to get big enough that it's going to almost probably reach pretty close out to our orbit. What happens when a planet it becomes inside of its star as its star is expanded? We're not totally sure. But looking at the physics involved, some planets maybe will, if they're in thin enough atmosphere of the star, will continue around just like nothing's ever happened. They'll just be, cooked cinders orbiting inside their star. Other planets, their orbits will probably degrade a little bit because of the friction with the atmosphere in the star, and they might spiral into the star. Will Earth's orbit change? Probably a little bit, probably not tremendously. It will change a little bit, but what will be a bigger problem for us is the fact that we won't have oceans or an atmosphere. The Earth will be cooked. Hopefully, by that point in time, that's a good ways away, right? 5 billion years. Humans will have figured out how to travel through the stars, and we won't be just strapped here to our own solar system. All right, let's look at the stars we see in the night sky. Now, I mentioned this already. We're on number 11 here. When you look up into the night sky, you don't get a correct sampling of the stars that are really out there. And it's confusing because you look out at the night sky, and most of the stars that you see are upper main sequence stars and red giants, really big stars, bright stars. Not surprising, right? They're bright enough that you can see with your naked eye. If we really just take a sampling of stars that are nearby us, there are far more red dwarfs and white dwarfs than there are anything else. So those big supergiants, those big giants, the upper main sequence stars, there's really not many of them. But there are loads of those lower mass stars. They're just so dim it's hard to see them. Now, why are there so many more of those lower mass stars? The main reason is because they live so much longer than the large mass stars. So that's why there's more of them. It's just the problem is that the bigger mass stars are easier for your naked eye to see. So that's the answer to number 11 there. All right. I think we answered number 12 as well. Okay. So we primarily see the high mass stars because they're brighter, but low mass stars are actually way more common in our galaxy. In two reasons for that are one, because first of all because they live so much longer, and also it seems because it's easier for low mass stars to form, so we get more of them. Okay, ready to move on here. Okay, so looking at number 13 on your paper there, stars are huge. I mean, some of them are 7 times the mass of our sun, or many times more than that. How in the world can something that big actually run out of hydrogen when the entire thing is basically hydrogen, right? Well, the reason that stars, really large stars, run out is because the gases don't mix. So it's the core that runs out of gas. The core runs out of fuel. There's plenty enough hydrogen out there. It just doesn't mix very well with the inner parts of the star. So there's actually different types of heat flow going on inside a star. Down deep in the core, there's convection. So it's mixing kind of like a boiling pot of water. The gases are mixing around and getting used. Then there's this radiative zone where light, photons, heat is radiating outwards through the majority part of the star. And different stars can have some vastly different types of heat transfer depending on when you look at them. If you look at those little, say, 0.5, 0.2 solar mass stars, there's considerable mixing going on in other parts of the star, not just down there in the core. So they can tend to live a lot longer because of that. So why does a star run out? Because the fuel doesn't get mixed, so it can't fuse. Okay, the fusion's happening for the most part down there in the core. Okay, so taking a look at these guys here, there we go. Those littler ones tend to have a lot more mixing, like those 0.2 solar mass stars, way more mixing going on. Okay, oh, there we go. I forgot I did that. Low mass stars mix their fuel well, so that's one of the main reasons they do live so long. They've got a lot to burn. Okay, so number 14, when hydrogen's fused, the main product is helium. What's happening to the helium? So we've kind of talked about this a little bit already. The core of the star, as it's fusing the hydrogen turns to helium and starts to fill up in the core. Remember, helium is further down on the periodic table, right? Number 2 rather than number 1. So helium's heavier, and it falls to the center of the star where all the gravity is. And it becomes what we call helium ash, okay? Um, it's not going to fuse right away though, uh, because it needs to get considerably hotter before it will do that. Okay. Um, so the rising temperatures, though, inside the star that are just outside of the core itself with all this ash in it, uh, are able to ignite what we call a hydrogen fusing shell. So originally, hydrogen's fusing down there deep in the core, but after the core fills with the helium ash, hydrogen can really only continue to fuse just outside of that. So you have to look at stars kind of like onions, like ogres, right? There's layer after layer after layer inside of a star, and different things are happening in different layers. So the fusion has basically moved into a layer outside the core. Now the picture is not to scale, so it's kind of confusing. This is actually a very, very tiny, tiny, itsy bitsy little part inside of this giant star. That's actually the core and the fusion that's going on. Okay, so what's happening now is the star is beginning to produce more energy than it needs to balance its own gravity, and it's actually going to expand. Okay, so the hydrogen shell is burning there in a red giant. You can see there, so it expands, it cools in the outer part of the star. We've got this helium-rich core that's building up, getting dumped in there, and the hydrogen's fusing just outside of that. Okay, okay. Um, so what's happening to the helium? It's becoming helium ash uh, inside the core. It's falling down into the core. Okay. So the direction, number 15 here, the direction that a star moves on the HR diagram as it expands into a red giant. We've kind of already mentioned this, but as a star expands into a giant, it both becomes more luminous and redder, okay, because the outside cools down. So you could look at color, you could look at temperature, luminosity. The direction that a star is going to move off of the main sequence is going to be up and to the right. Okay. Now, does it really move in space? No, it doesn't really move in space. Okay. Um, it just moves on the diagram, right? So uh, when what do I have written here? So the lack of core pressure causes more contraction, generating greater heat and bringing the burning hydrogen shell closer to that heat. Okay. More and more energy is generated at an even faster rate, flooding energy into the outer layers of the star. So the star is going to heat up down there in the core, and it's going to expand. Um, Here we've got a picture of a protostar dropping onto the main sequence, um, and then of course being on the main sequence for the majority of its life. If it's a G-type star, maybe 10 billion years. That's our sun. And then evolving rapidly off of the main sequence and becoming a red giant. When it ends its red giant stage, it's going to become a white dwarf. So we'll talk more about white dwarfs here in a little bit. Okay, so here's where I have that. The expanding star's surface cools, which moves it to the right side of the HR diagram. So if you're looking at the picture of our sun there, the star, when it starts to expand 5 billion years from now, it's going to slide off to the right of the diagram, but at the same time, the surface area is going to increase a lot, making it more luminous and causing it to go up the diagram because luminosity is going upwards. Okay, and what that explained to Hertzsprung and Russell was that all these weird stars that were in these kind of groups that were off the main sequence, it explained how they got there. Because there's some weird groups, these white dwarfs, these giants, these supergiants, kind of explains to us how they ended up where they're at. Okay. Okay. Now we're going to talk about some stuff that's a little more complex. Last couple questions here. We're going to talk about degenerate matter and how it kind of differs from a normal gas. Okay, so I'm going to say this first here. Describing electron degenerate matter. for number 16 there, essentially what it is matter, atoms, right? Nuclei, atomic nuclei, that are packed so tightly together that their electrons refuse to get any closer. So it's matter that electrons have packed as tightly together as is possible, as per the rules of quantum mechanics. So this is a little bit uh, interesting because we've started out talking about stars that we can describe quite well with things like Newtonian physics. We talk about their large masses and their gravitational force and how they're moving through space. And now we're describing stars and we're talking about parts of them that are so small we have to talk in terms of quantum mechanics. So, what's going on deep down inside this star? We have to think about the layers that are forming here. The hydrogen's fusing into helium, and the helium's accumulating in the core as ash. Okay, so this is 100% helium core now. Uh, the core is being crushed by gravity because it's not exerting pressure. The helium's helping to or the hydrogen's helping to exert pressure because it's fusing, but the helium is just sitting there being worthless. So I guess in a sense you could consider it a degenerate in that matter, right? But that's not really what electron degenerate matter means. What electron degenerate matter means, of course, is that the electrons are just packed as tightly as is allowed by quantum mechanics. So, the core is actually becoming more dense, and this is kind of strange because normally when we think of an object getting more massive, we think about adding more stuff to it so it gets bigger. Like you put more stuff, you make a bigger star, it's more massive. Um, However, with degenerate matter, it's kind of weird because it's actually getting smaller. It's getting compressed so tightly together that it's becoming more dense, and it's not getting larger. So, electron degenerate matter is some real weird stuff. Uh, the pressure that's exerted here is not from moving atoms like in a gas, but from the quantum mechanical effect where there's just a limit to how tightly electrons can get stuck next to each other. Um, so when we compare this, think about this in terms of other states of matter that you understand a little bit. You're used to talking about things like solids, liquids, gases, even plasma, right? Uh, those things are vastly different from degenerate matter. Um, as a gas is compressed, uh, it gets hotter, right? So, in terms of degenerate matter, the gas is so compressed that the particles are bumping right up against each other, and they start to behave much more like a solid. A normal gas will exert greater pressure the hotter you get it. So think about it kind of like this. If you were to take a sealed container of gas and throw it in, say, a fire. Now, don't do that, right? It's very dangerous because what's going to happen if it's sealed and there's gas in it, the gas is going to heat up. The gas molecules, they're going to start bouncing around inside the container until their pressure is so great that it's going to explode. And shrapnel is going to go everywhere, right? So, we wouldn't want to do something like that, but it serves as a good point of as you increase the pressure, right, or the temperature, the pressure of the gas increases, right? Now, degenerate matter is different primarily. One of the main differences from a regular gas is that it doesn't depend on temperatures. Pressure doesn't depend on temperature. You can increase the temperature all you want, and it doesn't push any harder out against the can. Not that there's any inside of a can. Wouldn't be possible, but it doesn't push outwards at all the hotter you get it. In fact, degenerate matter is a fantastic conductor of energy, of heat. So that's going to kind of come about here in a little bit about when we talk about what's going to happen to this degenerate core here, because this is not the end of the story. But if you want to get that down for number 17 there, how does degenerate matter differ from a normal gas? The primary difference is that while a normal gas exerts greater pressure with higher temperature, a degenerate gas, pressure does not depend on temperature. You can make it as hot as you want, it's not going to exert any more pressure at all. the pressure that it exerts, the only way that it's supporting the star at all, is that it just refuses to collapse any further. It's just packed as tight as it can be. Okay, so what we're using to describe all this stuff are quantum rules, and here they are over here. So this is a little bit more advanced, but essentially what has happening here is that moving particles can only have a certain amount of energy. And there's things in quantum mechanics, there's characteristics that we call spin, and particles of opposite spin can only occupy a single level. So if you look up there at my little goofy little picture there, a regular gas has a lot of unfilled energy levels in terms of its electrons or where they're allowed to be. But in a degenerate gas, all those lower levels get filled with two particles of opposite spin. So you can't put another one, you physically, by the laws of physics, can't put another electron in there any closer to the atomic nucleus. It's already full. It won't get any closer. So how closely the particles are spaced kind of depends also on their masses. These really low mass electrons are spaced a little bit further apart than higher mass neutrons that we're going to find out kind of is what happens to this star here in a little while. But this is our degenerate matter. And I think we are done with this lecture. Good. Oh, one more thing there. Nope, that's it. Yes, as the core heats up, most of the energy is absorbed by the nuclei, speeding up their motions. Electrons can't absorb enough energy to jump up to a higher energy level, so their temperature does not increase. But the key takeaway is that pressure does not depend on temperature in degenerate matter. All right, guys, have a good day.